All right, today we're doing something a little different. We're going to put you right in the hot seat for a simulated technical interview. And the topic? It's one of the absolute cornerstones of machine learning, linear algebra. So let's dive in and see if you've got what it takes. So picture this. You've made it all the way to the final round. The only thing standing between you and your dream job is this one conversation. The interviewer leans in, smiles, and says, "Let's talk about the fundamentals. So how do you make sure you absolutely ace this?" Let's walk through it.
Okay, so here's the first question. Can you define vectors and matrices for me? And more importantly, can you explain their geometric interpretation? See, this isn't about just spitting back a textbook definition. It's about showing that you have a deep, intuitive feel for these concepts. At its core, it really is simple. A vector? It's just a list of numbers. You can think of it as an arrow pointing from the origin to a specific point in space. A matrix is just a grid of numbers, right? But the real magic, the part that matters, is what happens when you bring them together. And this is really the key, the most important intuition. A matrix isn't just a static grid of numbers. It's an action. It's a verb. When you multiply a matrix by a vector, you're not just doing arithmetic. You are fundamentally transforming that vector. You're stretching it, squashing it, rotating it, maybe flipping it around. Every single algorithm, from basic regression all the way to massive neural networks, is built on this simple, powerful idea. So this whole idea of transformations, well, it leads us directly to one of the most famous concepts in all of linear algebra. The interviewer follows up, "Okay, good. Now what about eigenvectors and eigenvalues?" This question right here is where you really start to separate yourself from the people who just memorize the formulas. You know, the formal definition is all captured in this one simple-looking equation. But what is it actually saying? It's saying that for some special vectors, we'll call them V, when you apply the transformation A, you get the exact same vector back, just scaled by some number, lambda. The vector's direction doesn't change at all. And that's a huge deal. Here's the best way to think about it. If a matrix is some sort of transformation, like a stretching and rotating of all of space, the eigenvectors are the special directions that just don't get knocked off their axis. They are the unshakable axes of the transformation itself. They might get stretched longer or squished shorter, but their direction is locked in. That's why they're so fundamental. So why does this matter for your interview? Well, because these unshakable directions pop up absolutely everywhere in machine learning. For principal component analysis, they are literally the directions of the most variance in your data. In graph algorithms like PageRank, they tell you which nodes are the most important. And in deep learning, they can even help us understand if our model is stable while it's training. The interviewer is nodding, impressed. Excellent. Now let's talk about the big one, singular value decomposition, or SVD. Why is it considered so fundamental?
This is often called the most important tool in a numerical toolkit, so you gotta know it.
So SVD lets us break down any matrix A into three separate, simpler actions. You have U and V, which are special rotation matrices. They just handle all the spinning and turning of space. And then, sandwiched right in the middle, you have sigma. And sigma is a super simple diagonal matrix that only does one thing, scaling. The numbers on its diagonal, the singular values, tell you exactly how much to stretch or shrink along each of those new axes. What this really means is that SVD gives you the complete, step-by-step geometric recipe for any linear transformation. It's like the ultimate instruction manual. And it's always the same three steps. You rotate the space, then you scale it, and then you rotate it again. That's it. Every single matrix transformation, no matter how wild and complex it seems, is just those three simple actions in disguise. And the power here is just immense. I mean, unlike eigendecomposition, SVD works on any matrix, rectangular, square, whatever. It's also incredibly stable for computers to calculate, which is huge in practice. And it immediately gives you vital information, like the true rank of the matrix and the absolute best way to approximate it with a simpler version. Okay, so the theory is great, but now it's time to actually apply it. The interviewer says, "Perfect. Let's walk through two practical scenarios to see how you'd really use these concepts." First up, a real classic. You've got a data set with way too many dimensions. Explain to me step by step how you would use SVD to perform principal component analysis. This is the kind of question that tests if you can connect a powerful algorithm to a core everyday ML task. And the answer is just so direct and elegant. First thing you do, you prepare your data by centering it. That just means you subtract the mean from each column. Then, you simply compute the SVD of that centered data matrix. And honestly, the hard work is already done. The columns of that V matrix that SVD spits out are your principal components. They're the directions of highest variance all lined up for you. So if you want to reduce your data to, say, k dimensions, you just take the first k of those columns and project your data onto them. It's just a beautifully clean and efficient process.
Now for the final question. The interviewer wants to connect the classic concepts to what's happening right now, on the cutting edge. How does a fundamental idea like matrix rank show up in state-of-the-art deep learning models? So first, a quick refresher. The rank of a matrix is basically its true dimensionality. It's the number of independent directions it can actually map vectors to. And a super easy way to find it? You just compute the SVD and count how many of the singular values are not zero. And this idea is absolutely critical in modern deep learning. You can think of a layer's weight matrix as an information bottleneck. Its rank determines the maximum amount of distinct information that can even flow through it. This is the whole magic behind techniques like LoRa. Instead of retraining a massive billion-parameter model from scratch, LoRa just freezes the original weights and learns a tiny low-rank update. It's way more efficient. And what's really fascinating is that researchers are finding that even when models are way over-parameterized, they often tend to learn low-rank solutions all on their own, which might be a key to why they generalize so well. You've nailed every single question. So, to close this out, let's just zoom out for a second and summarize this single biggest takeaway from this entire conversation. What's the real big picture here? Here it is. The big takeaway is that linear algebra isn't just another tool in the toolbox or a prereq you had to get through in college. It is the language of machine learning. It's the architectural blueprint. These vectors, these transformations, these decompositions we've been talking about, they're the very building blocks that define how our models perceive, process, and ultimately structure information about our world. And that just leaves us with one final thought to chew on. We've built these incredible things using the geometry of vectors and matrices, but as AI keeps pushing boundaries, what new mathematical blueprints are we going to need to design the models of tomorrow? Now that's a question for the next generation of interviews. Thanks so much for tuning in.